First of all, just our quick reminders that we've had here the last few days. Today is the last day to withdraw, so if you are in a situation where you are contemplating withdrawing from the class, I do actually have office hours after class today, and I would be happy to talk with you if you are in a position where you are considering that. We do also have these extra credit opportunities that are available. We have talked about them the last couple of class periods. If you want to know more about them, go back and review the notes that were posted for the last couple of days, and you can find out more information about them there. So, with that said, today, this is our topic, and I do realize that there's probably a few people gone today. I've gotten some emails about some ACT testing or whatever that's happening, and some that may be coming in late or whatever. Anyhow, today I often say is one of the probably the most theoretical lecture of the semester, and it is based on the concept of electronegativity. And so we're going to start by defining what that is. We define the electronegativity like this. We define it as being a relative measure of the attraction an atom places on shared electrons. So it's a relative measure of the attraction, if I can spell it right. There we go, attraction that an atom places on shared electrons. And of course, if we're talking about shared electrons, that means that this is going to be most important to which types of bonds? Is it most important to ionic bonds or to covalent bonds? Well, which one involves shared electrons? Covalent. So it's going to be most important as it applies to covalent bonds. And in particular, we start by looking at nonpolar bonds. Now, I put in parentheses here pure covalent because this is what your author calls them. Your author calls them pure covalent bonds, but most chemists refer to them as nonpolar bonds. And a nonpolar bond is one in which the electrons are shared equally. That's why it's not nonpolar, because it's not like one has them more than the other. We use the term polar. It's kind of like our politics today. Seems like if you don't have one view, you have the other extreme view. And so in a polar bond, this is when electrons are not shared equally. So again, electrons not shared equally. And when you came in here today, I had you, if you have your textbook available, open up to page 341 in your text. Page 341 shows a table of electronegativities. And this table is one which omits the transition elements in the center. And for at this level, that's fine. We don't need to go very much into depth. And we also do not see electronegativity values given for the noble gases. So in the absence of those, in fact, these don't have electronegativity values because, of course, if we go back to how we defined the electronegativity, we define it as being a relative measure of the attraction an atom places on shared electrons. What is it that these elements don't do right here?
They don't share.
Yeah, they don't share and they don't transfer. They don't do anything. They don't form bonds with other elements. Now there are some exceptions. We just mentioned what they are. It does turn out that these three elements, the krypton, xenon, and radon, they do actually, all three of them, bond with fluorine, and xenon and radon will also bond with oxygen. But other than those exceptions, the helium, neon, and argon, they do not bond with anything. And again, the last three here, the krypton down to radon, they will form bonds with fluorine, and xenon and radon will bond with oxygen as well. Now, as far as what I'd like for you to know about the table of electronegativities is this. You do not need to memorize specific values. However, I would like for you to know the general trends in the electronegativities. So that is, if you don't have the values available, you should know the general trends. And that is, if we go across from left to right, what happens to the electronegativity values? They increase. And as we go down within a group, what is the general trend? They decrease. So that's what you should know. You should know the general trends. That is, again, the electronegativity values increase as you go across from left to right in the periodic table. The values tend to decrease. I mean, there are some exceptions, but the general trend is that they decrease as we go down within a group. So now, if we go back to how we define these terms, and that is the terms polar bond and nonpolar bond, and if we talk about what these electronegativity values represent, the larger this value, that is, we see that fluorine has the largest value. The larger this value, the greater its attraction for shared electrons. And the lesser the value, the lesser its attraction for shared electrons. So again, big values, big attractions, little values, little attractions. And it should be no surprise when we talk about ions, if we were. Now remember, this is more important when we talk about covalent bonds. But notice with the large electronegativity values, these here are ones that have greater attractions for electrons, is what it boils down to. And the metals here then would have lesser attractions for the electrons. So if we came back then and we wanted to determine the polarity of bonds, let's say that we had a bromine atom bonded to another bromine atom. Now we're just talking about one atom bonded to another. We're not talking about a complete molecule. But if we had one atom bonded to another in these, what we'd do is we'd look up those electronegativity values. In fact, we wouldn't even need to look it up for two like atoms bonded together, because if we had two like atoms bonded together, they would automatically be which type?
Nonpolar.
They'd automatically be nonpolar, because they are going to share electrons equally. Their electronegativity values are the same. So we would say that these have a nonpolar bond, or your author would refer to it as a pure covalent bond. Again, we wouldn't even need to look up the electronegativity values because they would be the same. But if we did, we'd see that all bromine atoms have an electronegativity value of 2.8. Then if we looked at a bond between nitrogen and chlorine, here if we wanted to determine whether it's polar or nonpolar, we come back to our table of electronegativities. We see that nitrogen and chlorine both have a value of 3.0. They both have a value of 3.0. This bond here is going to be nonpolar once again. And then if we looked at a bond between sulfur and fluorine, we would see that sulfur has an electronegativity of 2.5, fluorine at 4.0. So this bond then would be one that is polar. And it's because they have different electronegativity values. Now, your textbook does go further, has a table right below this table of electronegativities, and says, well, actually, if we go between 0 and 0.4, we call it nonpolar. It goes from 0.4 to 2, we then call it a polar bond. And if the electronegativity value is greater than 2, then we say that that is an ionic bond. And I really don't care that you know this 0.4 value in here, because for it to be truly nonpolar, its electronegativity value should be identical or very, very close. So And depending upon the author, you might see someone will call it 0.2, others will call it 0.5. It really is an arbitrary cutoff. So just for the sake of our argument, when it comes to our exams and when it comes to your homework, I've tried anyhow to make sure that it's very clear that if they're identical, then it is going to be a nonpolar bond. And then if it's going to be in this range right here, where there's a large difference, or a difference between them, then it's going to be a polar bond. And then if the difference is really, really large, then it's going to be an ionic bond. And the only time we have a really big difference between them is if we combine a metal with a nonmetal. And all along we've talked about them as being ionic bonds anyhow when we combine these metals with the nonmetals. The reality is, and this really only matters to chemists, it doesn't matter to you guys, the reality is that there's really no such thing as these bonds that are purely covalent unless they have identical electronegativities or pure ionic. The reality is that there's always some mixture between them. There's always some sort of blend. And if you get into more advanced chemistry, we might talk about something like the percent of ionic character. And so really there's never really anything that's truly 100% ionic. And there's never really anything that's truly 100% covalent unless we're talking about one where there's pretty much identical atoms bonded to each other. So if you are going to learn any difference, just know this one right here. That kind of 2.0 is that cutoff between ionic and covalent in terms of bonds. But even then, it's going to be ionic if you have metals bonded with nonmetals, and so there's really not much point to really even distinguish between them. So what we're going to do from here then, turns out that the polarity of bonds is not the most important thing. What's most important actually is the polarity of molecules. And so we're going to distinguish between molecules that are polar and nonpolar. And to determine whether molecules are polar or nonpolar, I can give you some definition, and if I would, here's what, don't write them down though, but here's what the definitions sound like. We talk about a nonpolar molecule. We describe a nonpolar molecule as one that has a symmetrical distribution of electrons within the molecule, and a polar molecule is one that has an asymmetrical distribution of electrons. But that doesn't really mean anything unless we look at some actual structures. So that's what we're going to do, is we're going to look at some actual structures, and based on looking at the structure of the molecule, we should then be able to determine its polarity. And so we're going to start by looking at HCl. And actually I'm going to write down several. What I'm going to do here is I'm going to write down the Lewis diagrams for each. Even though you've done these before, we'll just go through and we'll write out the Lewis diagrams. This is for HCl. I remember that chlorine has an octet. Hydrogen has what we call a duet. And hydrogen's outer level is filled with just 2 because the first energy level holds a maximum of 2 electrons. All of the other outer levels have a maximum of 8, but the first level will hold just a maximum of 2. Then if we looked at bromine, Br2, we would have drawn out a Lewis diagram looking something like this. And then if we drew out water, this is one molecule which I expect you to know the shape of. Horrible grammar, but that's what I expect. Not the grammar, the shape of the molecule, right? So what is the shape of a water molecule? Is it linear or is it bent?
Bent.
It's bent. Okay? And so this is the one that I expect you to know the shape, and you must know that water is a bent molecule. Then we have carbon tetrachloride. For carbon tetrachloride, we put the carbon in the center, then surrounded by the chlorine atoms. And we put in the dots around each of these chlorines. And let's see, what else do we have? We have nitrogen trichloride. Now for the nitrogen trichloride, what I'm going to do here is I'm going to go to some molecules. I've built these three-dimensional molecules and put them up here electronically. In fact, here's the HCl that we looked at before. Here's our Br2. Here's the water that we looked at. Here's the carbon tetrachloride. But now to get the correct shape down for the nitrogen trichloride, we kind of look at it here, we should see that this nitrogen kind of sits on top of the plane. It might be easier to see if we just look at the stick model, so we can see that that nitrogen sits kind of above there. And so we'll put down the nitrogen trichloride, showing its correct shape right here. So we'll show the nitrogen above the three chlorines. And then we'll put in the dots. And then we'll do the same thing here for the ammonia, which is NH3. If we look at the shape of an ammonia molecule, we see that ammonia as well has a shape kind of like a tripod, that nitrogen sits on the top. So again, we'll write out the nitrogen, and then we'll show it above the three hydrogens. Okay, so now what we want to do here is we want to determine the polarity of these molecules. Now, to determine the polarity, we go back to our table of electronegativities. We need to look up those electronegativity values. So in HCl, we look up the electronegativity of the hydrogen and the chlorine. And we see that we have value of hydrogen of 2.1. Chlorine we have 3.0. So I come back here. We have hydrogen sitting at 2.1. Chlorine sitting at 3.0. Then the next thing we're going to do is we are going to determine the polarity of the bonds. Is this bond going to be polar or is it nonpolar? It's going to be polar. It's going to be polar because these values are
vastly different.
They are different from each other. And because they're different from each other, that means that this bond is going to be polar. So now, when we have a polar bond, we want to assign what we call partial charges. And these are not going to be complete charges because this is not an ionic bond. The electrons are not transferred from one to another. But rather, we go back and remember what the electronegativity stand for. Since chlorine has a large value, this means that the electrons spend more time with the chlorine than they do with the hydrogen. And if we think of the term electronegative or electronegativity, that means that this chlorine is going to be one that's more apt to have a negative charge. So we label it with a partial negative amount. And the hydrogen is going to have a partial positive charge. Now, if you make it into calculus, you're going to learn that these symbols represent a Greek letter delta, and they stand for partial amounts. And this means that this is partially positive, this is partially negative. It's not a complete positive, not a complete negative, but again, the one with the largest electronegativity value is always going to be assigned a partial negative. So if you remember what the word is called, electronegative, the one with the greatest electronegativity is going to be the one labeled partially negative. So now, once you have them labeled, here's how we determine the polarity of the molecule, which is the most important piece of this. What we do is we take a plane that is a flat surface, and we see if we can separate all the positive atoms on one side, all the partially negative atoms on the other side. We can separate the partial positives, the partial negatives, using a plane like we have here, then we have a polar molecule. And that's exactly what this is. This here represents a polar molecule. And it's polar because we have the partial positive hydrogen on one side, the partial negative chlorine on the other. Now if we go back to bromine, we have two like atoms bonded together. That means that the bond between them is a nonpolar bond. The bond is nonpolar. We can't assign partial positive or partial negative. So if all of the bonds in a molecule are nonpolar, that means that the molecule is nonpolar as well. We cannot put any partial positives and partial negatives in here again because these two atoms will share electrons equally. So it's an equal sharing. We don't even need to look up the electronegativity values because two like atoms bonded together will always share electrons equally. Well, then we go to H2O. We look up the electronegativity for hydrogen and for oxygen. We see hydrogen here at 2.1, oxygen sits here at 3.5. So again, hydrogen sits at 2.1, oxygen sits at 3.5. Now of course this time, we have two bonds that are in there. So when we have two bonds, and we want to look at the difference in electronegativity, we actually want to determine the polarity of each bond. And we compare them one at a time. So if we wanted to look at this bond, we basically cover up the other one. We don't divide up the electronegativities, we always compare these values. So if these values are different, then this bond is going to be a polar bond. The one that gets labeled partially negative is the oxygen. The hydrogen gets labeled partially positive. We do the same thing here. We label them. Oxygen is going to get labeled partially negative. The hydrogen here partially positive. And again, that's simply because we compare these values. So we don't really show like there's two partial negatives, but we simply label it. It's a partial negative here in the oxygen, and each of these hydrogens is partially positive. Then we use the plane test. We want to use the plane test. And the plane test basically says if we can use a plane to separate, get all the partially positives on one side, the partial negatives on the other, then we have a polar molecule. So in this one here, we use the plane test. Here's our plane. And we get all the partial positives on one side, the partial negatives on the other. Yes or no?
Yeah.
Yes, we can. That means that this molecule here is a polar molecule. So again, water then is a polar molecule. Then we go to carbon tetrachloride. In the case of carbon tetrachloride now, we want to determine its polarity. And to determine the polarity of carbon tetrachloride, we look up the electronegativities of the chlorine and the carbon. So here we've got the carbon sitting at 2.5. We have the chlorine sitting at 3.0. So carbon sitting at 2.5. Chlorine sitting at 3.0. Well, then we start assigning partial positives and partial negatives. Partial negative goes to which element?
Carbon.
Partial negative goes to chlorine. Okay? Partial positive then would go to the carbon. Now, since we're drawing this in 2 dimensions, it might actually be easier to look at the 3-dimensional molecule for carbon tetrachloride. Let's zoom in on this right here. And now, let's try to find a way to get all of the chlorine atoms on one side and the carbon atom on the other. Is there any way we can divide this up to get all the chlorines on one side and the carbon on the other? It doesn't work. And so even though the bonds in this molecule are polar, the molecule itself is going to be one that is a non-polar molecule. So again, this one here is going to be a non-polar molecule. I hate when this thing does that. Non-polar molecule. And so again, this is a case where the bonds are polar, but the molecule itself is non-polar. In fact, we even really wouldn't have needed to look up the electronegativities of this one, because all we'd have to do is to look at the shapes of the molecules. And if we look at the shape of the molecule, we would see that no matter how we put this, no matter how we put it, and try to look at it, that carbon's always going to be in the center, and it's surrounded by chlorines the whole way. There's no way we can get this so the carbon's on one side and the chlorines are on the other. So that's regardless of whatever those electronegativity values would be, we look at the shape of the molecule. Then we go on to the nitrogen trichloride. In the nitrogen trichloride, this one here, we look up the electronegativity values. We see that nitrogen sits at 3.0, the chlorine sits at 3.0. So again, coming back here, nitrogen's at 3.0, chlorine's at 3.0, which means all of the bonds in this molecule are non-polar. If all of the bonds are non-polar, that means that the molecule is non-polar as well. So this here is a non-polar molecule. So any questions on any of them that we've done here? Yes, Dave.
So basically, whenever it's non-polar, it's always going to be non-polar?
Exactly. If, like in these cases here, you're talking about when the bonds are non-polar.
Yeah.
Yeah, if the bonds, if all the bonds in the molecule are non-polar, then the molecule is always non-polar.
Okay.
However, if the bonds are polar, then what do we need to do?
Check to see if you can split them.
Right, then we need to check the shape of the molecule. That's where the three-dimensional shape comes into play. So here we can split them. We have the negatives on this side, the positives on this side. This one here we can split them. Positive on this side, negatives here. This one, though, we can't split. So even though the bonds themselves are polar, the molecule is still non-polar because of that three-dimensional shape. Okay, anybody else? Yes, Gloria?
How do you put the delta plus and the delta negative again?
Okay. What do we call these values here? Remember what they're called? They're called the electronegativity. Okay? So, this is a mnemonic. This is a mnemonic, memory aid. So if you think of the word electronegativity, you have to remember that word, electronegativity. The one with the greatest electronegativity is the one that signed a partial negative charge.
Okay.
So just think electronegative, partial negative. Big electronegativity, partial negative is the one that's assigned. And so if one is the partial negative, then by default the other one is the partial positive. Okay, anybody else? All right, we've got a bunch of questions coming up in your Socrative app. Let's pull out your app here, and we have a question waiting for you. Well, maybe not waiting yet. It's going to be there in a couple seconds. Here we go. And this one now, just avoid the temptation of looking at that table in your text if you have it open. Based on what we learned, you can look at this periodic table. This is what it would be like on an exam. So if we do not have a table of electronegativities, and you look at the periodic table, which element would you expect to have the greatest electronegativity? Now you can talk with it to your neighbor about it, and I know you can look it up, but try not to look it up. See if you can remember how we determine. Remember that this is my mode of taking attendance, so let's get signed in if you have not yet. All right, and we'll give you about 15 more seconds here. Count down. 5, 4, 3, 2, 1. And it would be oxygen. Remember that electronegativity values increase as we go from
left to right.
Left to right. And as we go down within a group, the electronegativity values will decrease. So if we're looking at these 5 elements right here, that means that using carbon as a base, they decrease going down and they increase going to the right. So that would put oxygen in the position of having the largest electronegativity value. Next up, in molecules of NH3, and I'm going to show you that structure again here in just a moment. In molecules of NH3, and now you can use your electronegativity table if you need to, the bonds between nitrogen and hydrogen are they nonpolar, are they polar, or are they ionic? So if you need the electronegativity values, hydrogen sits here at 2.1, nitrogen at 3.0. So are the bonds polar, nonpolar, or are they ionic? And here are the values. We'll give you 10 seconds to lock in your answer. And we'll count down. 5, 4, 3, 2, 1. They are polar. And they are polar because the electronegativity values are different than each other. That's it. So hydrogen's at 2.1, nitrogen's at 3.0. So in NH3, the bonds are polar. So next up is NH3, comprised of nonpolar molecules, polar molecules, or ions. Now for this one, it would be helpful to know its three-dimensional structure. Here's the three-dimensional structure for ammonia. I'll show you here what it looks like with the sticks. See, nitrogen kind of sits above the rest of them. Okay, talk over with the neighbor if you need to. And we're going to count down here. We got 5, 4, 3, 2, 1. It's comprised of polar molecules. Now, this one's polar, because again, the three-dimensional shape is critical to this one. If we looked up those electronegativity values, we saw nitrogen again set at 2.1. Chlorine, no, what is this? Hydrogen, what is it? I forgot them again. Nitrogen was at 3.0. Hydrogen is at 2.1. That means that the nitrogen here is partially negative. Each of these hydrogens are partially positive. And now if we can take a plane and separate all the partial positives on one side, all the partial negatives on the other side, then we have a molecule that is polar. So again, this is a polar molecule. If this is a flat molecule, then it's going to be nonpolar, but because that nitrogen sits above that partial negative, that makes this a polar molecule. Let's try another one. Next up, we have carbon dioxide. If you want to know the structure of a carbon dioxide molecule, here's what that looks like. Notice now that this is a linear molecule. We look at it like this. We can see it's still linear no matter how we look at it. So carbon is in the center of this. First question is, are these molecules, not the molecules, are the bonds polar or nonpolar? Bonds polar or nonpolar? And we'll give you about 5 more seconds. We'll count down. 5, 4, 3, 2, 1. The bonds are polar. And why are the bonds polar? They have a different electronegativity values. If we come back here, the electronegativity of the carbon sits at 2.5. The oxygen sits at 3.5. Now, I intentionally didn't tell you the values this time. We wouldn't need to know the values because what could we just simply do?
Look at the periodic table.
Look at the periodic table and remember that the values will increase as we go from left to right. So if we're going from left to right, we automatically know that oxygen has larger electronegativity value than does the carbon. If it has a larger electronegativity value, that means even without writing these numbers down, we could assign partial charges. Oxygen would be partially negative. The carbon would be one that is partially positive. Okay? So next question here on the Socrative app. Carbon dioxide. You need to know the three-dimensional structure. Here's what that three-dimensional structure looks like. Carbon dioxide comprised of polar molecules or nonpolar molecules. I think what's happening is you guys are getting the terms bonds and molecules mixed up. We consider the polarity of them independent of each other. This one here now is asking about the polarity of the molecule. And we'll count down. We'll go 5, 4, 3, 2, 1. And these are nonpolar molecules. And now in this case, the molecules are nonpolar because if we try to separate positive and negative, one side on the other, what happens?
You can't do it.
You can't do it. No matter how we try to slice it here, the negatives are on opposite sides of each other. And so now another way you can think about this is you kind of think about it as like a tug of war. You can kind of think of these numbers over here as kind of be a strength at which these atoms can pull. So carbon's at 2.5, oxygen sits at 3.5. The difference in here is 1.0. And so what happens is that this oxygen atom is tugging electrons this way. This oxygen is tugging electrons this way because each one of them wants those shared electrons, but they are tugging against each other with an equal strength. If they're kind of pulling on each other in equal strength and their sides opposite of each other, their net effect is to cancel each other out. And when they cancel each other out, that's going to make them a nonpolar molecule. So, any questions on any of these examples? Any questions? All right. Well, here's one you might ask. Who cares? I really don't care. Why should you care? Okay. Well, I'm not going to say that you'll care more after we look at this, but it is something that helps describe what it is that we observe. And it's the three-dimensional structure of the molecules that help us describe what these things do. And this is a general solubility rule, and that general solubility rule says likes dissolve likes. Likes dissolve likes. And what this general solubility rule means is this. It means that substances comprised of nonpolar molecules tend to dissolve in other substances comprised of nonpolar molecules. And substances comprised of polar molecules tend to dissolve in other substances made of polar molecules. Again, we're talking about the polarity of the molecules, not the polarity of the bonds. So again, substances made of nonpolar molecules tend to dissolve other substances made of nonpolar molecules. Substances comprised of polar molecules tend to dissolve other substances made of polar molecules. And then it turns out if a substance is really polar, it can also dissolve ionic compounds. So very polar substances can dissolve ionic compounds as well. So that said, what I have up here is a couple of burettes, and these burettes are filled with two different liquids. One of the burettes contains water, H2O, and the other one contains hexane. So one is water, one is hexane. And since we're going to have a test on this here next week anyhow, let's see if we can remember how we write out the formula for hexane. Hexane is going to have how many carbons?
6.
6. And what else is going to be in this compound?
Hydrogen.
Hydrogen. And so we simply surround it then with hydrogens all the way around here. So hexane is going to look something like this. Now we already talked about the polarity of water. How about the polarity of hexane? Is this going to be a polar molecule or is this going to be non-polar? Well, we don't even need to look up electronegativities for this one. Because if it's polar, we should be able to separate atoms of one type on one side and atoms of another type on the other side. And can we separate carbons on one and hydrogens on the other? No. That must mean that hexane is a non-polar substance. So, when we look at water before, we said water is a polar substance. So here's what we're going to do. In these burettes, again, I have these two liquids, and I have them up here on the webcams. And what we're going to do here is we're going to see if we can, oh great, we can see that liquid really well. Come over here, let's make sure we can see this one. Yeah, we can see those. So we'll come back to this first one. What I'm going to do now is I'm going to take this balloon and I'm going to rub it in my hair to build up a static charge. And you're going to watch this on the screen. I'm going to put the balloon up to this liquid. We should see that nothing here happens to this one. So we'll come to this side here. We now see the liquid. I don't know if you can see that. Oh, sure you can. What's happening to the liquid when I bring the balloon up there?
It's diverting its path.
Diverting its path. So, first question here is this, and this is Socrative app. Which burette contains the water? The first one, which there was no attraction, or the second one, which there was an attraction? Can talk over with the neighbor if you need to. And let's see here what you guys said. We'll give you about 5 seconds to lock in an answer. We'll count down. 5, 4, 3, 2, 1. And the second one was the water. And we would expect water, of course, to be attracted towards the comb because water is comprised of polar molecules. If it's a polar molecule, those have your partial positive and partial negative charges, and that then is going to be attracted towards the static charge that's built up here in the balloon. Now, I can also bring this over here and put it by the faucet. This is one of those things that you can actually demonstrate at home. This is what I call my kitchen chemistry demos. And if I move this aside here, what you're going to do, if you want to try this out at home, just try to get a thin stream of liquid coming out of a faucet, rub the balloon in your hair, and you should see, we'll do it this way, there we go, and you should see here how the water is attracted towards the balloon. And that's simply because of the static charge that we built up in the balloon and the fact that water is comprised of polar molecules. Okay? Now, as long as I have this here, we might as well just demonstrate this. I forgot to do this at the beginning of the hour. This was the setup we had left at the end of our last class period. Remember now that we have water in the liquid phase. This is water in the gaseous phase, and that we have now let this come to room temperature. Now this worked this morning. We'll see if it works. I need to be careful because it's probably going to jump out of the stand like that. So again, we're boiling the water without heating it. I love it. All right, so now let's see, what else do we have? Oh, next question. I am putting some, and you don't need to answer this one yet, but what I'm doing here is I'm putting some water and hexane into these test tubes, and I'm trying to put approximately equal amounts into each one. So I put the water in here already. And somewhere I must have walked off with my other stopper. Here's one stopper. Here we go. All right. Okay, so now we have the water and hexane. And remember that water, we say, is what type of molecule? Polar. And hexane is? Nonpolar. So what's going to happen if I shake these up? Will they dissolve in each other? Or what should happen once I'm done shaking?
They'll separate.
They should separate if we have any luck here with this. It looks like, in fact, they are separating. We're getting the two distinct layers back. So then the next question is, which layer is on top? I have the density information there. Which layer is on top? Take a look at your Superintendent app. Density of hexane is 0.66 grams per cubic centimeter. Water is 1.0 grams per cubic centimeter. That means which layer is on top? Then what I'm going to do here, while you're answering that, oh, looks like we're all locked in. We'll check it out. All right, of course, hexane, because hexane is less dense. That should be the one on top. So now, what I'm going to do here is I have some iodine, which is I2, and I have some cobalt-2 chloride here, which is an ionic compound. I'm going to place these into these two test tubes, and then I'm going to shake it up. And so, according to the general solubility rule, likes dissolve likes. Therefore, I2 should dissolve in which layer, and cobalt-2 chloride should dissolve in which layer. And I'm doing the iodine on your left. Get your answers locked in before I actually do this. Talk it over if you need to. These are test questions here, guys. You will need to know this. This explains why things dissolve in your body and why you should avoid certain things. So we'll give you about 10 more seconds. And we'll count down. 5, 4, 3, 2, 1. And then we'll look at it. This is how we're going to answer this one. Here's the iodine. This one is going into the one on your left. And then we will put the cobalt-2 chloride, the one that's on your right. And the reason why I picked these out is because they have kind of this nice pink and purple color. So again, iodine is on your left, cobalt-2 chloride is on your right. So now I'll start shaking. Again, we can see the nice colors that are forming once they start dissolving. And if we stop these, we'll see that the iodine went into the hexane layer and the cobalt-2 chloride went into the water layer. And let's see how we did here on our questions. All right, looks good. And I2 went into the hexane because hexane is nonpolar, iodine is nonpolar. Water is polar. Cobalt-2 chloride is, it's not actually polar, this one is actually ionic. But because water is a very highly polar substance, it will also dissolve ionic compounds. So any questions on the demo here for today? Okay, next up then what we're going to look at is intermolecular forces. And intermolecular forces, if we analyze the name, intermolecular forces mean that we have forces that act between molecules. Because the prefix inter means between. So these are going to be forces that act between molecules. And they're broken down into two main categories. They are van der Waals forces. And we skip down a couple lines here. We also have hydrogen bonding, or hydrogen bonds. And van der Waals forces consist of two subtypes. They are what we call dipole-dipole forces and London forces. And London forces are not named after the city of London, but rather after a person who is given credit for first describing them. Sometimes London forces are also called dispersion forces. We're going to start by looking at dipole-dipole forces. Dipole-dipole forces. Now if we analyze the word dipole, dipole would imply that we have something that's comprised of two poles. It's going to be polarity, exactly. It's going to be a polar molecule. Something that has two poles. And so dipole is the same as a polar molecule. Because a polar molecule has two poles. It has a partially positive pole, partial negative pole. And so these here are forces that act between polar molecules. Now if we were to give an example, we could look at something like HCl. And in HCl, we've already drawn out the structure for HCl. We have a structure that looks something like this, H-Cl. We show the extra dots around the chlorine. If we go back to our previous example on these, we saw that hydrogen had an electronegativity of 2.1, and the chlorine had an electronegativity of 3.0. Which means that these chlorines would get labeled partially negative, hydrogens get labeled partially positive. Now if we had more molecules of HCl, those additional molecules of HCl would line up in a very predictable manner. And they would always line up in a manner such that the partially positive hydrogen of one atom is always near the partial negative atom of a different molecule. And so if we went one more level right here, let's say we had another layer of HCl, the other layer would look something like this. And the reason why the other layer looks something like this is because, again, the partially negative chlorines of one molecule are going to have an attraction for the partially positive hydrogens of a different molecule. And so, well, if I went through and finished labeling all of these here, we have something like this. And so now what I'm going to show, let's put this here in a kind of a, maybe this blue color. What I'm showing here in blue now represents these intermolecular forces. And this basically is representing an attraction that occurs between the atoms of these different molecules. There's an attraction that exists here. There's another one that exists here because there's a partially positive chlorine of one molecule attracting a partially positive hydrogen of a different molecule. Where again, those little squiggly lines that I've drawn, and this is my way of representing it. What this represents is a dipole-dipole force. And again, it's simply an attraction between a partially positive atom of one molecule and a partial negative atom of a different molecule. And again, dipole-dipole forces act within these polar molecules. Now we're going to contrast that with London forces. If we look at London forces, which again we also call dispersion forces, these are forces that are present in all molecules, but they're the only force present in nonpolar molecules. So they're present in all molecules, that is polar and nonpolar, but they are the only intermolecular force present in nonpolar molecules. Now, for these, we give several different types of examples. We could talk about something like H2 or carbon tetrachloride. We could look at helium atoms themselves as being attracted by the London forces. Once again, basically anything that is nonpolar. If we look at something like helium atoms, these are the easiest to look at. We could look at the construction of a helium atom. And to look at the construction of a helium atom, we look at what's in the nucleus. And how many protons would be in the nucleus of an atom of helium? So go back to the periodic table, and we look at helium. How many protons would we find in the nucleus? It'd be 2. I'm just showing 2 positives. And if we had another helium atom, there'd be 2 protons in the nucleus of a neighboring helium atom as well. But then if we start putting in electrons, helium is also going to have 2 electrons. Now ordinarily those electrons would be randomly distributed within the helium atoms. We don't know exactly where they are because the motion of electrons is random. And so at any point in time they could be like this, they could be like this, any possible position they could wind up orienting themselves into. But let's say all of a sudden that they wind up moving so they are both on the right-hand side of this first helium atom. Well, what happens then is that this side of the helium becomes partially negative and this side over here becomes partially positive. Partially negative simply because they have the negatively charged electrons. Well, then we remember what we learned earlier this semester, and that is like charges tend to repel each other. And so these electrons are going to tend to repel electrons in a neighboring helium atom. So it could wind up something like this. This makes this partially negative, that makes this side partially positive, and as a result, then there winds up being an attraction between the 2 helium atoms. And that is an example of a dispersion force. But because these electrons are moving rapidly in here, at the very next instant in time, they could wind up having a more symmetrical distribution of electrons. It gets rid of the dipole, it disappears, and we're back to something like this, and there's no longer any attraction that's present. At the next instant in time, maybe this particular helium atom winds up with electrons that are distributed like this. If that's the case, the left-hand side of this helium atom requires a partially negative charge. The right-hand side is partially positive. These negative charges will repel the electrons in a neighboring atom, making this side partially negative, this side partially positive. And as a result now, I have a partial positive and a partial negative near each other. They then will wind up attracting each other. But again, this is only going to be something that's very temporary in nature. At the next instant, it needs to go back to more even distribution, and there's going to be no longer any attraction that occurs between them. And this is something that we're showing only 2 atoms. Remember that in real substance, this is going to be something that's in 3 dimensions. And so there's going to be attractions that are going to be occurring in all different directions, and when they do occur, they're going to be very, very temporary because of the constant motion of electrons in these atoms. Now, I do have an animation that shows this here and shows the difference. This first animation is one that's showing dipole-dipole forces, and as they come into the screen here, the blue portion represents the partially positive portion, the red here represents the partial negative portions, and the glowing yellow represents those dipole-dipole forces. And you can see here that there's a continuous attraction that occurs between the partially negative portion of the one molecule and the partial positive of a different. And once again here, as they wind up going off the screen, they do have that attraction for each other. When we compare that to the London forces, and the London forces, this here is showing a molecule of hydrogen, or H2, and when you see it getting fat, that's where those electrons are in the same hydrogen atom in that molecule. And you're going to see that when it gets fat, it's also going to be kind of reddish color, which is kind of that buildup of negative charge. And there's only going to be attraction that occurs whenever the partial negative of one is near the partial positive of the other. But again, it's only something that's temporary, and it disappears as those electrons move about randomly within the molecules. And so the London forces, again, one of the things that makes these London forces a little bit weaker is because these London forces are only temporary. They exist temporarily, then they disappear. They exist again, then disappear. Exist and disappear. And it all has to do with the random motion of electrons within those molecules. And then the last one that we'll look at here today is called hydrogen bonding. And in hydrogen bonding we say is a special type of dipole-dipole force that is very strong and it occurs in molecules where hydrogen is directly bonded to either nitrogen, oxygen, or fluorine. So again, it has to be one in which the hydrogen is directly bonded to either nitrogen, oxygen, or fluorine atom. And so then the first question is going to be this: what is it that's so special about the nitrogen, oxygen, and fluorine? Well, we look at where they're located on the periodic table. We see they're all kind of located right here in the cluster. But the other thing we should see is that these three elements have the three highest electronegativity values. Now you might contend that chlorine is also up there because its electronegativity is the same as nitrogen. But chlorine does not exhibit hydrogen bonding simply because nitrogen can make up to 3 bonds with hydrogen, whereas the chlorine can only make 1 bond with the hydrogen. So it's only when these 3 elements are bonded directly to the hydrogen. So again, that key when we talk about it, directly bonded, that's another important thing. Because if we look at these two molecules have an identical number of carbons, hydrogens, and oxygens. However, only one of these two would have hydrogen bonding. They both have 2 carbons, 6 hydrogens, and 1 oxygen. Which one would have hydrogen bonding? Would it be this one here or this one here? And why this one?
Because it's one hydrogen is bonded to the oxygen.
Right, this one here is the hydrogen directly bonded to the oxygen. This one here, the oxygen is bonded to the carbons. It's not bonded to the hydrogen. So this one here is one that has hydrogen bonding. Now, one of the things that this implies, or what happens, is that it turns out that this one here we've already talked about before. This one here is ethanol. This one here is a liquid at room temperature. This one, even though it has an identical molar mass, identical number of atoms, this one here is a gas at room temperature. So the fact that this one has strong attractions between the molecules is one of the things that causes this one here to be a liquid at room temperature. And we talk about life. We talked about water and its importance to life in here before. We'll talk about it again. Here's another reason why when scientists look for life in other parts of the universe, why we always look for water first. And it goes something like this. First of all, now we're not looking about water at all. Let's just talk about intermolecular forces. These here represent the elements of group 14. That's these elements right here. These are the elements of group 14 if they're bonded with hydrogen. All of these here are going to be nonpolar molecules. And if we did a plot of their boiling point versus their molar mass, their boiling point is going to increase the heavier they become. And that's very easy to explain because if things get heavier, it requires them to take in more energy. They use up more energy when they're heavier. And trust me, I used to weigh like about 100 pounds. I have to eat a heck of a lot more now that I'm more than twice that to keep going. So again, we might compare it to like car engines. Bigger cars have bigger engines because they require more energy. But now something interesting happens. These plots here now are plots of the elements of group 17, no, what is it? Group 15, which would be nitrogen, phosphorus, arsenic, and antimony. This one here is the plot of group 17, which is the elements fluorine, chlorine, bromine, and iodine. And the one in green here represents the elements of group 16. These are all if they're bonded with hydrogen. Now, if we ignore these three, we would see that all of them follow the same general trend that we just observed before, and that is as we increase the molar mass, we also increase their boiling point. But what do these three here have in common with each other?
Hydrogen.
Well, they all have hydrogen, as do all of these here. But our topic of the day today is electronegativity and, more importantly, intermolecular forces. So, in terms of intermolecular forces, what types of intermolecular forces do these three here all share in common with each other? These are ones that all have hydrogen bonds. These all three have hydrogen bonding. And if we ignored hydrogen bonding, that is, if hydrogen bonding didn't exist, what would happen is we'd see the boiling point of water right about here, the boiling point of HF about here, and the boiling point of NH3 about right here. All those boiling points would be way down here. And all of these would be gases at room temperature. But water is a liquid at room temperature because of the fact that it has very, very strong attractions between other molecules of water. And I understand we're going to run over here about 1 or 2 minutes today, but I just wanted to show one quick point here as to why this is. If we looked at molecules of water, and we talk about where this hydrogen bonding comes from and why it's so darn strong, let's consider a whole bunch of water molecules together. And if we had a whole bunch of water molecules together, they would always orient themselves in such a manner that an oxygen atom of one molecule is always near a hydrogen atom of a different molecule. An oxygen of one molecule is always near the hydrogen of another. And that's because if we looked up those electronegativity values, we see that oxygen sits here at 3.5, hydrogen sits here at 2.1. So we have hydrogen at 2.1, oxygen at 3.5. If we label the partial positives and partial negatives, we'd have oxygen sitting here, partial negative. In all of these cases, hydrogen is always going to be partially positive. What's going to happen then is that there's going to be the strong attraction that occurs between these molecules of water. And that attraction is going to be strong because this difference in electronegativity is a difference of 1.4. And this here is a big difference. This is a big difference. And the larger that difference makes these molecules more polar. And the more polar they are, the stronger they're going to attract each other. It's just like if we dumped a whole bunch of magnets into a bucket, they're going to attract each other. Now we compare it, instead, let's say we replace this oxygen with something like sulfur. If we replace it with sulfur, come back here to sulfur, which has electronegativity of 2.5, the shapes of these molecules are all going to be identical, except instead of having oxygen in here, we now have sulfur in there. They're still going to have attractions for each other. These attractions will exist, but instead of having a difference of 1.4 in electronegativity, the difference here is only going to be 0.4. That 0.4 is no longer a very big difference. It's a very small difference. They are going to have some attraction for each other, but that attraction is not going to be very strong. So in the case of water, water is very unusual. It has that very large difference in electronegativity. As a result, it is sitting way up here in terms of its boiling point because its molecules very, very strongly attract each other. And that's part of what makes life responsible here on Earth. The other thing is, just a minute here please, is if we look at the shape of those water molecules, this is what water looks like in the solid phase. For most substances, if we have a solid, they're going to be packed together. But water here, if we kind of turn this around and we look at this, we're always going to see that there's an oxygen of one molecule near hydrogen of another. Oxygen, hydrogen, oxygen, hydrogen. And that attraction is what holds them in place. And those bent molecules actually gives water a density that is less dense as a solid than it is as a liquid. In other words, ice floats. And as we talked about before, that's yet another reason why water is unique and why we look for it when we look for life elsewhere. So, any questions? I know I kept you a minute or two over. Any questions here today? All right. That's it here for today. We'll be having a test next week.